Okay, so, my voice still kind of sounds like crap because I've been sick, but we must go on. This is a video on 1.5. If you're watching this and there aren't any other videos out, just hang tight. There is two videos coming. One for a method for sign charts and one for a study guide for units 1.1 through 1.5. Or 6. 6, yeah, it's 6. So 1.1 through 1.6. So just keep an eye out for those. They're not going to come immediately because it's a lot of work to get these out, but let's start. So, topic 1.5. The main thing in topic 1.5 is multiplicity. Now, what is that? What is multiplicity, and why is it important? So, now, I've drawn a really, really sad-looking graph here, and I've put the corresponding equation. And I want to point out something that's really interesting about about multiplicity. So we know it's about the zeros. So we've got a 0 here, a 0 here, a 0 here, right? And if you look up above, there's 3 of these. So what's interesting about multiplicity is that the intersection of the line with the axis resembles the function with the degree that is multiplicity. That sounds really, really complicated. Okay, it's really simple. So this has a multiplicity of 1, right? And x plus 4, you know how to expand that. It's x plus 4 equals 0, minus 4, minus 4, x equals negative 4. So this corresponds to this point right here. And if you'll notice, it just looks like a line. There's no curves, there's no nothing, it's just a line. Like a linear function. Now what's the degree of a linear function? x1, right? Because it's just mx plus b. That's the highest degree it goes, so it's a first degree function. So if you have a 0 with multiplicity of 1, it's going to look like this. It's going to look like it just goes straight through, right? Now let's look at this. X plus 1, which we've done this before, we can imagine what happens. It's x equals negative 1 for the 0, right here. Now you notice this right here looks an awful lot like a cubic function, right? Cubic function. And would you look at that? It's got all 3 right there. So the multiplicity will make it, at least up to 3, will make it look like the type of function that that degree makes. So again, with the square. The square here is just downward parabola. Bounces off, doesn't touch it. This is the maximum for that parabola. That's it. And that makes it a lot easier to identify. The other thing is, obviously, you need to check the exponent on the actual terms. And it's not always going to be this simple and given to you. For example, if we were to go down here and give another problem, I'll let editing magic do this. Okay. Okay. So we've got a new problem here, and you notice there's no graph to go along with it. Now that's fine, because most of the time we're not going to have one, and we don't need one. That trick earlier was it's just a nice little thing to know, just to kind of check your work, just something fun to know, something to keep on your mind. This here is more like what you're going to see. And one extremely important thing you have to remember is that if there is an x just on its own, just chilling, that is a 0. 0 is a 0, right? Because if you think about it, we're trying to find instances where if we were to turn x equals to 0, because what actually is a 0, right? A 0 is when y equals 0. And that could happen when this x right here is equal to -1, because -1 plus 1, that's 0, and then 0 multiplied by the whole expression, that's 0. And that's how these zeros work. But right here, if x is equal to 0, the exponent, the 2, doesn't matter. Just all turns into 0. And then multiply it with everything else, that makes 0. So that means this expression actually has 3 zeros. So we have, right here we have -1, because remember, you always have to invert this. You have 0 from this, and you have +4, because you invert it. Now, one little notation thing I like to do is put, instead of putting multiplicity 1, for myself, I just put m, let's see, this is m1, this right here has a 3, so it's m3, and then this one here has a 2, so it's m2. Just something to see. And we'll be using these later. This is just something to do. And this is how you'll take apart these expressions to get all the zeros, so you can process them later. One extra thing to consider is imaginary numbers. Now, imaginary numbers come when you have an equation that goes like this, and then you're like, where does it touch 0? It doesn't. So, but you can't just not do that. You can't just not touch 0. In those equations, it has to have some solution. So, the solution is imaginary numbers. It's just like tacking a band-aid on it, you know? So, for every imaginary solution, there is a second. There's a kind of pair to it. So, if we were to have the solutions for this graph here, right, they would be imaginary. So let's just say it's 4 plus 2i. Now, the order here is important. And the reason for that is because all complex numbers, and a complex number is a number that goes a plus bi. It is a constant added to an I, which means imaginary, with a coefficient. Coefficient with an I always comes second. That's just how that works. That's a complex number. So if we were to say this is our only root of this equation here, like that's it, we'd be wrong. Because we need our pair, conjugate pair. Now, conjugate pairs sound really complicated, but they're very simpler. They're very simple. All you have to do, flip the sign. Only the sign. The sign in the middle is the only thing that matters. Think of it like you're changing what's inside of the sandwich, right? You're not changing what's on top of the bread, what's in the bread. Nothing in the bread changes. You're just changing what's in the sandwich. So 4 minus 2i. Boom, pair. So it's 2 roots. That would be your answer. You'd have 2 roots, and those would be it. That's the conjugate pair. Another example, you might see one that starts with a negative. So 4 plus 2i. Same drill. Change what's in the sandwich, not what's around it. Right? Undo. For some reason, my Control Z doesn't work when I'm full screened. It's really weird. So the conjugate pair for here, still -4. It would just be minus 2i. No big deal. Just change what's in the sandwich, that's all. Moving on here, we have, let's see, I have the packet in front of me. I am just looking at what we've got. Yes, sign charts. Now, I hate sign charts. Me personally, I hate sign charts. And I'm actually going to be covering this in a second video. Now, I'm going to add, now hopefully, if I'm smart, I added like a thing at the top of the screen that like links you to the video. If I didn't do that, just check the channel. It's probably there already. But it's a way simpler, easier way to do sign charts, and it'll cover solving nonlinear inequalities it'll help you with all that. That's really good. So just check that out if you need help with that. But for now, I'm just going to go over determining the degree of a polynomial given a table of values. So let me just draw this out for you. I'll be right back. Okay, we're back. So if we wanted to determine the degree of this table right here, it looks like a bunch of gibberish. Because normally you're used to going through and being like, okay, first you check if they're in equal intervals. So you go, this goes up by 2, this goes up by 2, this goes up by 2, this goes up by 2. Okay, we're good, right? Equal intervals, so we don't have to do any fancy math or anything. So -2 to -3, that's -1. -3 to -1, that's 2. -1 to 4, that's 5. And then 4 to 12, that's 8. These numbers have nothing to do with each other, right? But do not fear, because that just means that this isn't a first degree polynomial. Now we do it again. -1, 2. That's 3. 2, 5. That's 3. 5, 8. That's 3. Huh. So that must mean it's a second degree. And the way you know what degree it is because if it was all the same values, it would be a 0th degree. Because it's just like y is equal to 6. It don't matter. There's no x. X's degree is 0, which makes it 1. So really, there's nothing. So it's just 6. That's if all these values were constant. If these values are different, we do this thing where we determine the distance between them and we put it on the side. Distance, put it on the side, distance, put it on the side. Now here, it would be a first degree if these were all the same number. Right? And let me give you an example of that. So if we had 1, 2, 3, 4, 5, and then we had 8, 10, 12, 14, 16, right? It's not 0th degree because they're not all the same, but the distance is 2, 2, 2, 2. Oh, look, all the same. First degree. First degree polynomial right there. But here, they're not all the same. So we do it again. And this is second degree. And now you'll notice that here it looks like if we were to graph this out, when x equals 1, it's -2, -3, and then we go to -1 to 4 to 12. That looks a lot like a parabola, which is a second degree, right? And that's how you find out the degree of a table, of a polynomial from a table. Now, what if we're a higher degree? What if we're like way higher than this, right? Let me draw you out a new table. Okay. Now, you may or may not have done this one already, but when you look at it it's like, what is this? Right? But we just tackle it the same way we would any other problem. First, you find if they're equal intervals. They are. It's equal, right? Next, are they all the same? Is it a 0? No. Let's check if it's a 1. So we go up by 2. We go up by 10. We go up by 17. We go up by, how much is that? 23? 23. Not a first. They're not all the same. We do it again. Up by 8. Up by 7. Up by, how much is that? That's 3, 3, that's 6. Getting closer, but still, they're all different. Let's do it one more time. That's -1, and that's -1. 3. And keep in mind, depending on the degree of the polynomial, you just keep going. You'd be all the way out here if you have enough items in the table. Obviously, we're not going to be doing that, but you get the idea. You just keep going up until you find where you're at. So we got a third degree polynomial right here. And of course, if we were to graph this out, I don't even know if we have enough information for it to look normal or like a cubic function, but I'm going to give it a try. So 0, -2, and then we go to 3, and we're at 0, right? And then we go to 6, and we're at 10. So we really went up here. And then 9, we're at 27. So, yeah, I could see that being a cubic function. I could see this going down, and then that being your standard shape, right? So it checks out, right? So this is a third degree, and that is how you find the degree of a polynomial from a table. Okay, properties of functions. Very easy section, in my opinion. Essentially what it's saying is, let's say we have a function here. Whoa, scary, so many numbers. But remember, I always have this on every board. Brave. Read and reread the question. You need to understand what they're asking you for before you get scared of the question. Let's say they're asking you, is this polynomial even or odd? You know what an even number is, right? You know what an odd number is, right? Just look at the biggest number next to an x, the leading coefficient, right here, and say, is that even or is that odd? That's all you have to do. So, is this polynomial even or odd? Looks even to me. And what's fun about even equations is, sorry, cut out there for a second. What's interesting about even and odd functions is that they follow some patterns. So let's go x1, x2, x3, x4, x5. And then you'll start to see the pattern with that. So x1, straight line, right? Goes both ways. x2, parabola, goes one way. x3, wobble line, goes both ways. x4, a parabola with brain damage, goes one way. x5, this weird looking thing, but it goes up. Seeing the pattern here? Odd functions will go both ways. They will go both up and down. They will not have a minimum, they will not have a maximum. They don't care. Even functions will always have a minimum or a maximum. Right? So, knowing that, and also another thing is that even functions tend to be symmetrical about the y-axis. The y-axis. So if we were to cut this in half, it'd be symmetrical. If we were to cut this in half, it'd be symmetrical. While odd functions tend to be symmetrical about the origin. So if we were to cut this in half like, let me use a different color. If we were to cut it in half like this, it's symmetrical. If we were to cut it in half like that, let me draw our other arrow. It may be weird, but it's symmetrical. Same here, right? So those are some rules about functions that you need to keep in mind. Anything else I didn't cover? Not really. 1.5 was pretty simple. I'm going to go quick review. So multiplicity. Okay, I'm coming back here to do a little bit more work on multiplicity because, let's face it, I probably didn't cover it in enough detail. So let's use a more complicated example. Boom. Big, chunky. All we have to do here is we have to find the degree of the polynomial and find the zeros and the multiplicities, right? Looks impossible, but let's just break it down. So first, immediately I can see that these are quadratics, and I like factoring. Factoring's fun. We love factoring. So how can we factor this? Now, I am probably going to make a video on the factoring technique I use. So if you don't follow, then just check that out. But if we see x, what are the factors of -8? We have -4 and 2. -4 combined with 2 gets you -2, so that works out. So we end up with x minus 4, x plus 2. Right? Okay. Let's factor this next one. X. And then if we have negative 4 and then 5, negative 4 combined with 5 is just positive 1. That's what we get. And so we have x minus 4 and x plus 5. This looks a lot more familiar. This is what we're used to dealing with. So now we need to combine like terms. And if you're thinking like, wait, why don't we just do zeros now? X minus 4, x minus 4. Same thing times itself is just itself squared. It's just squared. So 4x cubed x minus 4 squared. X plus 2, x plus 5. Boom, right? We factored that down. Now it's looking pretty. And now all we have to do is find the degree of the expression. So just count the x's. So 1, 2, 3, 4. This counts double because it's squared. All right, if we were to expand this, x minus 4, we get x squared. That's all we need. So we know that's x squared. So we got 1, 2, 3, 4, and then we got 5, 6, 7. Right, so 3, 5, 6, 7. Degree of this expression is 7. Okay, I got a cough drop. Sorry. Okay, so n equals 7. That's the degree of the expression. Now for the zeros. Obviously, 0 is a 0 because of this right here. So we have 0. We have negative 2. We have 4, and we have negative 5. And these are our zeros. So we have M3, M1, M2, because that right there, and M1. Perfect. That's about it for unit 1.5. Let me know if there's any questions you have. Oh, my throat hurts. So, I've been talking too long. Hope you enjoyed the video. I'm going to be coming up with more soon. But, yeah.